Okay, hi guys. This is a lecture video called Atomic Structure and Electric Force. We're going to start by looking at this simple circuit that we looked at in class briefly. We could see that there's a battery here within this circuit, and these little blue dots are going round and around. They're going through that light bulb and making it light up. Okay, this is an example of a simple electric circuit. Those blue dots represent electrons. What electricity really is electrons flowing through wires and then flowing through devices like light bulbs and doing work. They are transferring energy. They can cause things to move. They could cause things to warm up. They could cause things to produce light. Okay, so electricity is really a type of energy, but when we get down to the nitty-gritty, it's really just electrons on the move, electrons moving through a circuit. So I want you to take a look at this circuit and see the different things it contains: the battery, okay, the light bulb, and then those electrons flowing through wires. Because where we're going to start here is by doing a little drawing. So I want you to find this handout in your packet. This is for taking notes on. My notes will be on Google Slides. You can write your notes on this paper. The title here is Atomic Structure and Electric Force. Okay, electricity is based on this thing called electric force. Sections 1 through 3 in chapter 11. The basic question we want to answer today is, what makes those electrons flow through a circuit? What causes them to move like that? All right, so let's go ahead and fill some things in on this page, and then we'll get to the slideshow and have you go ahead and write notes from the slideshow. So electricity is basically electrons on the move. And this is a little different from static electricity, which is electrons that are staying still. But we saw in the John Travoltage simulation that those electrons build up, but when you do something like touch a doorknob, those electrons start to move. And that's when you get zapped. That's the electricity. It's those electrons on the move. So let's draw a simple circuit, a diagram of a simple circuit here. I'm going to start down at the bottom here with a very simple battery. I'm basically just going to draw it like a rectangle down here. And let's see, this end will have that little bit sticking out. This is the positive side. All right. This is the negative terminal on this battery. Up here at the top, I'm going to draw my light bulb. Here is the glass bulb part of it, and then down at the bottom is the metal piece where it screws into a socket. And I'm just going to put a little dimple there as well. So to connect the light bulb to the battery, we need some wires, and I'm going to have one wire coming from the light bulb this way, and it's going to be connected here to the negative terminal of the battery. And then a wire coming out of this part of the light bulb will be connected to the positive terminal of the battery. And then I'll go ahead and draw some electrons in here. Electrons are really way too small to be seen. Okay. But those electrons are going to be moving. Okay, and they're going to be moving in a particular direction. All right, and to understand which direction they're going to flow, you need to know a few things about electrons. For example, they are negatively charged. You also need to know one of the basic rules of electric force, which is that opposite charges attract each other, like charges repel each other or push each other away. So these electrons are going to be flowing in this direction away from the negative terminal of the battery. The battery is pushing them. The negative terminal of the battery is pushing the negative electrons away. The positive terminal of the battery is attracting the electrons toward it. So what we've got with this push and pull is motion throughout this circuit, in this case, going in a clockwise direction. So draw those arrows in there to show the direction of flow. Now, the way this electricity does work for us, it actually comes in through this light bulb, travels up through some wires and across the filament, and it's that filament that gets really hot, and so hot that it starts to glow and produce light. And then those electrons have to come back out through this other wire to continue on to the positive terminal of the battery. So the electrons are repelled or pushed away from the negative terminal of the battery. Okay, and they are attracted toward the positive terminal. That's the nitty-gritty, that's the basics of how electric circuits work. So now let's get into some more of the details. I am going to go ahead now and share my presentation with you. All right, and here we are. That should be working. So here we are with our title slide. Let's just go right on into it. So these slides or these notes are going to include these three basic sections. We're going to start with basic atomic structure because it's important to understand how atoms are put together in order to understand how electricity works. And then we'll talk briefly about what we mean by electric force, and then we'll get into something called Coulomb's law. Okay, here's a bunch of different representations of atoms. I think all of these are more or less familiar to you. I asked you to draw atoms in class. We haven't studied it yet, so here are a bunch of different representations I pulled from the internet. What do you need to know about the structure of the atom? Okay, we're going to be focusing really on this image here. Okay, this is the simplest one that we're going to use. The first thing you need to know is that atoms are made of three parts. They're called subatomic particles: protons, neutrons, and electrons. You could write these names down in the second box of your note sheet, numbers 1, 2, and 3. There's some things you need to know about each of these. Okay, first of all, where are they in the diagram? You're given a diagram on your paper. You should be able to draw that simple diagram and identify which ones are the protons, which ones are the neutrons, and which ones are the electrons. Notice that the protons and neutrons are in the middle. We call that the nucleus. Okay, the protons have a plus sign in them because they are positively charged particles, and you find those in the nucleus of the atom. They have a charge of +1. Often we'll see that written as 1 plus as the sign comes after the number. The neutrons are also in the nucleus, but they are neutral. They don't have a charge. They're not positive and they're not negative. They have a charge of 0. Finally, we have the electrons, and those electrons are flying around outside the nucleus, okay? And they go way out here and sometimes even a little bit further out. Sometimes they come in a little bit closer, but they're just zooming around out here, and they're zooming around so fast it's like a blur. If you could see them, it would just look like a cloud of blurry electron flying around out there, kind of like this image toward the bottom left. Now, those electrons are also charged. They have a charge of -1. Okay, and that's a really important piece of information to remember about them. Now, these electrons, they're zooming around really, really fast at the speed of light. Well, why don't they just fly away from the atom? They're not attached to the atom in any way. Why don't they just take off? Well, this is where one of the basic ideas of electric force comes into play. The electrons are negatively charged. The protons in the nucleus are positively charged. So that means they're attracted to each other. It's like those protons, that nucleus is holding on to those electrons, keeping them from flying away. It doesn't hold them in place. They're still moving around a lot, but they can't get away. Kind of like two magnets attracting each other. So the nucleus is that chunk in the middle where the protons and electrons are. And what we need to remember about those electrons is they don't fly away from the atom because that positively charged nucleus attracts them. They are attracted to the positive charged nucleus. So those electrons are negatively charged, the nucleus is positively charged, and opposites attract, opposite charges attract. So I said earlier, the nucleus and the electron are not connected, but in a sense they are. They're connected in much the way that you and I are connected to the Earth by gravity. We're being held together, keeping us from flying away. Okay, so what we need to know about protons, neutrons, and electrons can be summarized in this table. I want you to fill in on your paper the charge for each of these particles, which was given on the previous slide, the location in the atom, in the nucleus, outside the nucleus, and then let's also go ahead and put in the mass. And I will tell you what those are right now so you can fill them in on your paper. Protons and neutrons both have a mass of one atomic mass unit. You don't have to worry about that unit label right now. You could just put in the number 1 for each of their masses. The electrons, on the other hand, are so tiny that their amount of mass is essentially 0. The electrons have a mass of 0. It's not really 0, but it's so tiny that we don't even have to pay attention to it. So you can fill that in on your data table. Okay, let's move on to the next slide in the next box. This one's on the back of your note sheet. And this one is about quantity of charge. This is a very important topic because it's very similar to net force that we learned about last semester. And what we mean by net force is you can have a whole bunch of forces acting on an object, but you can combine them and come up with one amount of net force acting on the object. The same is true with positive and negative charges. There could be a whole bunch of charged particles in an atom, but we can combine the positives and negatives and come up with the net charge. And it works very much the same way as forces. To get the net charge, you just add up all the charges, but pay attention to the positive and negative signs. Electrons are negative, protons are positive. So how do we do that? Let's start with this simple atom over here. This is a helium atom. It has 2 positives in the nucleus and 1 negative electron. So we have 2 positives and 1 negative. You add those together, 2 plus -1 equals +1. This atom has a charge, a net charge of +1. Whereas this atom on the right has 1, 2, 3, 4, 5, 6 positives, okay, a charge of +6 in the nucleus, and then a charge of -4 in the electrons. So +6 plus -4 gives us a net charge of +2 for this atom. Okay, so again, it's important to understand that charges have quantity. They have a positive and a negative, but they also have a quantity, an amount, a number. And because they have numbers, we can add and subtract them. And it turns out that that quantity of charge becomes very important in determining how strong the electric force is. And that's our next topic. Okay, we are going to move on now to talking about electric force. We know a few things about what atoms are made of and how they're put together. Now let's look at electric force. First of all, its definition. Electric force is either attraction or repulsion between two charged objects. There always has to be electric charge involved, and they're either going to be attracting each other or pushing each other away. Remember, a force is a push or a pull. An electric force can be either one. And the two rules of electric force are probably already familiar to you. So fill in the blanks here on your paper. Opposite charges attract one another. So positive and negative are attracted to each other. Like charges repel one another. Repulsion here means pushing apart. Two negative charges will try to get away from each other, and so they push each other apart. They don't like to be near each other. So go ahead and define repulsion on your paper as well, and then we'll get on to talking about Coulomb's law. Coulomb's law is a scientific law that lets us quantify how strong that electric force will be, that push or pull between charged objects. Okay, so this image is not on your note sheet, but I want you to take a look at these. These two separate boxes really illustrate what we mean by Coulomb's law. Coulomb's law tells us how strong the, in this case, attraction between a positive and a negative will be. So here in this top box, we have three situations. In each case, we have one proton, one positive, and one electron, one negative. Since they're opposite, they will be attracted to each other. Which of these three situations do you think will have the strongest attraction? In situation A, the positive and negative are pretty close together. In situation B, they're a little bit further apart, twice as far apart. In situation C, they're really far apart. What do you know about magnets and how strongly they're attracted to each other when they're far apart? When they're far apart, the attraction is there, but it's so weak that you often can't even feel it. When they're close together, like in situation A, the attraction is much stronger. So this electric force, this electric attraction between positive and negative is going to be a lot stronger when the two charged particles are closer together than if they are far apart. The second box down below, the positives and negatives are all the same distance apart. They're all 0.2 nanometers apart. Which of these situations is going to have the strongest attraction? If you're guessing situation C, you are correct. In this situation, we have a charge of 12 plus. That's much stronger than the 6 plus or the 3 plus. Even though these negatives are all ones, one negative, one negative, one negative, because the positive net charge, the positive quantities here are so much larger in C, it's going to have much stronger attraction than in A or B. So here's what Coulomb's law tells us. Number one, the closer two charged objects are to each other, the stronger the attraction or repulsion between them will be, the stronger the force. The greater the quantity of charge, the more protons or electrons you have, the stronger the force, the stronger the attraction or repulsion will be. So Coulomb's law tells us the strength of electric force depends on those two things. how close together the objects are, and the quantity of charge. Does this remind you of something? It sounds a lot like Newton's law of universal gravitation, and it is very similar. And in fact, it has this formula, which is also very similar to Newton's formula for gravity. Instead of the big G, it has this small k here. And that small k just stands for a number, okay? We don't need to know what that number is, but it's a constant. It's always the same number. The F stands for, and you should go ahead and label these on your paper. The F stands for the strength of the electric force, and that will be in newtons. The D here represents the distance between the two objects, okay? And that's got to be squared. But this is the distance between the two objects, and that will be measured in meters. And then we've got Q1 and Q2. Those just represent the quantity of charge, how many protons or how many electrons you have. There are two of them because you always have to have two objects. This is a force of attraction or repulsion between two objects. So we need the quantity of charge of both of them, and we multiply them together. So the more charges we have, the greater the quantity of charge in either object, the stronger that force, electric force, will be. So there we have it. We've got the basic atomic structure, this thing called electric force, and then Coulomb's law, which helps us understand why the electric force is strong in some situations and weak in others. The next set of notes will talk about how this electric force can get used in a circuit, how it's used to push electrons around a circuit using, in a lot of cases, copper atoms, and those electrons on the outside of copper atoms jumping along from atom to atom. That's next time. For now, we have finished this particular lecture.